Hey, good morning, class. Hope you all had a good holiday weekend. Kind of feels like a Super Bowl hangover to me right now. Not drinking, just tired. So I don't know how you feel. I'm glad there's 12 of you here. So I'm happy to see that. Any questions over the problems that I asked you to take a look at last class? No? Is one okay? We have a ton of problems to do today. So we're just going to start grinding away at this. Today, we're going to finish up exponential logarithmic equations. The assignment will be given after class for this. It'll just come right off of that sheet that I gave you here. And then next class, we're going to do some applications, growth and decay models. And then our test is a week from today, I believe. Yeah, so Monday. So I'm going to get you a review something in the next 2 days. I'll get a review to you. And that way you'll have something to prepare for over the weekend. And the test will cover everything through 6.8. All right. So let's get going here. We're going to continue with examples. We were solving logarithmic equations last time. And so we're going to continue doing that. Let me take a look at the last one we did. I think this was the last one we did, where we had two logarithms. And we're trying to create that loop, but we have to make sure we have a single logarithm by itself. So we had to condense these two logs into a single log. So we used a property. It was property 9. Let me get to those properties real quick. Here are the properties. I've made a mess of this page, but we'll use these today. So I may as well copy this down. Let me copy this real quick. Okay, just in case I need this, I'll have it here. All right, so let's go. All right, so we got a log equation. We have two logs on the left-hand side. And so before I can use a loop, I've got to condense these together, right? So to put these two together into a single log, I'm going to use property, where is it? Property 10 backwards. So here, if we have two logs being subtracted, I can turn it into division inside of a single log. So let's go ahead and do that. I'm going to have log, single log, and then I'll have division inside. And it will always be the first log's argument, 2x, and then divided by the second log's argument. The argument is the thing that's inside the function. Okay, so that's what we call the argument. So we put the arguments in there and then equals 1. So we're pretty much there. We can create the loop. However, the log that we have does not have a base written down here, right? So when you see log and there's nothing here, what's the number there again? If it's just log?
10.
10, good. So we're gonna put, we'll just put it here just to remind ourselves. And then we do the loop. So we're gonna have 10 raised to the first power equals 2x over x minus 3. And 10 to the first power is just 10 equals 2x over x minus 3. Okay, well, this equation, when we've been doing logs, we've been getting different types of equations once we do the loop. We've seen linear equations, we've seen quadratic equations. This is what we call a rational equation. And so the way that you go about solving this, it just kind of depends on what you see here. What I'm going to do first is I'm going to clear the fractions. This is a rational equation. So I'm going to clear fractions. That's usually kind of the first technique or first step of solving a rational equation. So I'm going to multiply the left and right hand sides by x minus 3. And that has the effect of getting the x minus 3 to cancel on the right. Now on the left, I have to distribute the 10 through. So make sure you have that in parentheses or else it'll be wrong. So we have the 10x minus 30 equals 2x. And now we have a linear equation. So we're happy about this, right? So we're going to solve this linear equation. Let me subtract 8x, let me subtract 2x from both sides. That'll give me 8x minus 30 equals 0. I can add 30 to both sides, and I can divide by 8. So x is 30 over 8. Now we have to check this answer. Remember, we have to check it. So to check it, we just want to make sure that when we plug it into this, we don't ever get a negative number or 0 inside the logarithm. Miguel, I got your chat. Thank you. So let me just look at this. If I go log, let's see, if I go 2x, it's 2 times my solution, 30 over 8. Well, that's going to be a positive number, so I'm happy about that. Minus log, and then I have to do x minus 3, that's 30 over 8 minus 3, and then equals 1. Does that work? What's 30 divided by 8? That's bigger than 3, isn't it?
It's 3.75.
3.7. So 3.75 minus 3, that's a positive number. So checks out here, right? Both of those check out. So I know that that solution is valid. It should work. Questions? Condense the logs. In this case, it goes to division. Subtraction goes to division inside of a single log. Your new equation was rational. Off to the races with that. All right, same sort of problem here. We have 2 logarithms. We have subtraction between the 2 logs. So I will put them together. But notice it's a natural log, right? ln. So, okay, we're going to get 1 natural log here. We'll get division inside, x plus 1 over x. Those are the 2 arguments divided, equals 2. And now, since we're using the natural log and we go to use the loop, we have to realize that when you have the natural log, this base is actually what? What's the base of the natural log function?
E.
It's e, right? So this is e down here. So when we do our loop, e squared is this. So we get e squared is x plus 1 over x. Now, you can actually, leave it as e squared if you want. That would be like, just leaving it. That's kind of like you can write the fraction 1/3 as 1/3, or you can go like 0.333 forever. This is what we call the exact answer. And this would be, the decimal. So we can leave e squared as e squared, or we can get on our calculator and actually square it and get a decimal, but it's going to be an approximation because e goes on forever. There's no pattern to it. So it's kind of up to you. I'm going to leave it as e squared because, as you move on in math, a lot of times we don't like to approximate. We want to leave things exact. So just everyone keep in mind that e squared is just a number. That's all it is. So I'm going to clear the fractions. Multiply both sides by x. Right? That'll clear out the fractions on the right. On the left, I'm going to write it this way, e squared times x. I'm putting the e squared in front of x because, like, if I had 4x, I'd write 4x, right? I wouldn't write x times 4. It's normal to put the number in front, so I put e squared in front of x. Just trying to explain why I'm doing that. Okay, so that's that. This side here is just x plus 1. And now it seems weird, but we need to solve for x. So let me subtract x on both sides. Now be careful here. I'm going to do e squared x. I'm going to subtract x on the left side, subtract x on the right side. When I subtract x on the right side, the x goes away, right? So take x away here, take x away here, it goes away. Here, I cannot combine these together easily. I have to think about this. Can anyone think of how I can put these two together or what I can do on this side? I'm trying to solve for x. There's
Take
like
out the
10
x from both terms.
Yeah, factor out an x. Exactly. If we factor an x out, right, we'll be left with e squared minus 1 equals 1. Right, just pulled an x from both of those. And now this is x times this. E squared minus 1 is just some number, right? I don't know what it is, but it's just a number. So what I'm going to do now is I'm going to divide both sides by e squared minus 1. It'll cancel, and I get x equals 1 over e squared minus 1. And that's my answer for x. Kind of weird, right? It's kind of weird, but get used to that sort of thing, because that's an exact answer. There's no, we're not approximating this at all. This is what we usually are looking for in math as we move on. Okay, so does this answer work? Well, here's what I know. 1 over, well, e squared is like 2.718 squared. I know that that number is like bigger than 4. And then I take away 1. I know that that's still going to be a positive number. 1 divided by a positive number should be positive. So I'm just doing a quick mental check. This is a positive number. So if I go back up to my original thing and I replace that with a positive number and that with a positive number, then a positive number plus 1 should still be positive. And a positive number in here, well, it's positive. So the thing is, I'm plugging in numbers that aren't negative and they're not zeros. So I should be good with this solution. There shouldn't be any problems. So I'm done. Questions there? All right, moving on. Same sort of thing here. Looks like we've got 2 logs on the left equals 3. Let's condense those down. Okay, so if we condense those, this becomes log base 4. We're using that same property, that subtraction becomes division. 2 logs become 1. The x squared minus 9 goes on top, the x plus 3 goes on the bottom, and then equals 3. Now I can apply the loop. So I get 4 raised to the 3rd power is x squared minus 9 over x plus 3. 4 to the 3rd power is 64, right? Not 12. Don't make that mistake, right? It's 4 times 4 times 4, so 64 equals, and then over here, x squared minus 9 over x plus 3. There's actually 2 options at this point. We can clear the fractions right now, or does someone see another option? You recognize x squared minus 9?
You factor that and then they cancel out, wouldn't they?
Yeah, if you take this and you factor it as x plus 3x minus 3. You see that? That's a difference of squares. Then the x plus 3's just cancel. And so what you'd be left with is 64 equals x minus 3, which is pretty clean, wouldn't you say? Just add 3 to both sides and you get 67 is x. Now that's one way to do it. Let me show you the other way. Oh, by the way, would this answer work? Let's see, if I plug in 67 for x, 67 squared is huge. Take away 9, that's still good. It's still positive. And then 67 plus 3, yeah, I should be good here. Let me show you the other way we could have solved this when we had 64 equals x squared minus 9 over x plus 3. If we had multiplied both sides by x plus 3, you would have got, let's see, distribute through here, you would have got 64x plus, let's see, 180. I can't do math today. 180. I can't do math any day. 192, I believe, equals the right side. Right. So what's different about this and the way we did it up there is we have a much more complicated equation now, right? This is quadratic, which means you're going to have to move everything over to one side. So let me see. 201. So let me move everything to the right. I'm going to have 0 equals x squared minus 64x and then minus 201. And then you have to solve that. So you can either try and factor it, or you can do the quadratic formula. But you should get 2 solutions, right? You should get 2 solutions here. I believe it factors, but I only know it factors because I know this answer from up here. So I'm going to cheat a little bit. This should factor to be, let's see, x minus 67. And I think it's going to factor this way. Let's see, 201 divided by 67. Yeah, 3 times. So plus 3, something like that. And so you get 2 answers. Set those both equal to 0. You get 67 and negative 3. But what do you notice about negative 3? You can't plug it in, right? If you plug in negative 3 squared is 9, 9 minus 9 is 0. You cannot plug 0 into any log, right? The natural log of 0 is undefined. And you can't plug in negative 3 here either because you also get 0. So that solution is going to go away anyway, which is why this way was better, right? This way, not so good, but still got you the same answer. Questions there? Okay. I've got logs everywhere, right? And this is not necessarily a bad thing though, okay? Because I can put these 2 logs together. Because I have addition this time, I'm going to use the property where it's going to turn into a single log. Here the base is a, right? They're not even telling us a number for the base, they're saying a. And it's a single log, and inside that log goes these 2 things multiplied, the 2 arguments multiplied together. So x times x minus 2. But that must equal the log on the other side, same base a, of x plus 4. So we had a property. I'll give you a second to make sure you have that down. We have a property that says that, where was it here? It's actually not on this page. Hold on. Go back to this. Here it was, property 13. If log base a of x equals log base a of y, then the 2 arguments must be equal to one another. So if you have 2 logs equal to one another with the same base, then you can just set the insides equal to one another, which is what makes this problem actually not as bad as it looks. Oops, wrong page. Okay, so let me go to it. So since I have 2 logs with the same base equal to one another, I can just set the inside of this equal to the inside of that, right? Set those equal. So I'm just going to do x times x minus 2 equals x plus 4. And I hope that it's obvious that this is just going to turn into a quadratic, right? Distribute the x. Got a nice little quadratic here. Bring everything to one side. Everything to the left. That factors. I'm real happy this factors. I get 2 solutions. They are positive 4 and negative 1. Now, I said this in class last time, and I'll say it again. You do not look at these numbers and say, oh, if it's positive, it works. If it's negative, it doesn't. That is not what you ever do with logarithmic equations. You must always check these into the original expression. So let's think about if we plug in 4 right here for x. Yeah, that's a positive number. 4 minus 2. Yep, that's positive. 4 plus 4, positive. We're good. So we can keep 4. Now, -1, if we plug -1 in here, that's a problem. It doesn't matter. If it's a problem in one of them, we're done. But there's also a problem here. -1 minus 2 is -3, so that would be an issue. -1 here is not a problem, but 2 of them are already bad, so I'm going to throw that one away. I know it may look like if your answer is negative that you're going to throw it away, but I promise you there are some log equations where even when you plug the negative in, it's still positive, like it works out. I mean, like what's in the argument of the log still works. Questions here? The answer is 4. Good. Thank you, Javier. Oh, whoa. Okay. Why don't I give you some time? Why don't you think about this one? You might have to draw on some stuff we did last class, but hey, you know, you only had an Easter weekend to forget everything. So see how it goes, all right? I'll give you a few minutes. Why don't you let me know in a poll if you actually get to this answer? I think we'll go no longer than 5 minutes. Let's see how you do. All right, it's been 5 minutes. I'm showing that 4 people have it. I'm going to share the work with you now. Take a look at it. Take a minute to see if you can follow what I did. As you're looking at that first step where I push the 2 up, both those 2's got pushed up as powers. I'm using a very important property of logs there. I have to do that before you can put 2 logs together. You have to make sure that they both have the same coefficients. They both have to have a 1 in front of them. That's why I did that. And then I just squared the 5, which became 25. I squared the 100, squared the 10, which became 100. Now I can put the logs together on the left and right. Take another 30 seconds to look at that, see if anything there doesn't make sense. Okay, who has a question? Does anyone have a question about any of these steps? Anything in the red or blue or black?
I just have a question on like you moving it to the power. I was looking at my what's it called?
Properties?
Yeah, properties, but I didn't see it. I don't know if we were.
Okay, that's property 11. It's property 11, but I'm actually using it not from left to right, but from right to left. So if you have a number in front of a log, you can bring that number up as a power. And I put a star next to it, Dominic, because this property is going to be, I keep telling y'all how important this stuff is in calculus, right? I mean, we use this property all the time in calculus. Yeah, it's real important. So, okay. What else? Anything else on that one that you need me to clarify? When I got to the black equation, I could have cross multiplied, but I just decided to just multiply both sides by 100 because that's the LCD, the least common denominator. So there's a couple of different ways you could have done this. And then my answer 1/3, if I check it real quick, if I plug a third into here for X, I should have positive numbers there. So I'm happy about that. All right, does anyone need me to stay on this page? You ready for the next one? Ooh, okay. So this one's a little weird because check out the left-hand side. We have a 3 out in front of both logs. Both logs are in parentheses, right? So the log on the right, I can push that 2 up here if I want, right? I can make that 4 squared. So this can become log base 7 of 4 squared is 16, right? I can do that, but on the left, I cannot push that 3 up yet. I first have to distribute the 3 to both logs. And then I can push the 3 up. So this becomes log base 7 of x cubed minus log base 7 of 2 cubed, but 2 cubed is 8. And that must equal log base 7 of 16. We good? The 2 logs on the left can now get condensed down to a single log with division because there was subtraction between those logs. So I'll put x to the 8th. X to the 3rd over 8. And now, since we have the same log on both sides with the same base, we can just take the insides, right, and set those equal to one another. So we'll get x cubed over 8 equals 16. And what's 8 times 16? Because I'm going to clear fractions. So what do I get when I multiply 8 on both sides here? X cubed that's 80 plus 48, right? So that's, I believe, 128. Is that right? 128. And then what are we going to do now? What am I going to do?
Would you cube both sides? Or not cube, but
The cube root.
yes, sir.
The cube root. Okay, so we're going to get x equals the cube root of 128, right? The cube root. So I'm basically taking both sides and I'm taking cube root. Now, when I do the cube root, do I have to do plus or minus? Don't remember? Only on even roots. So if you do a square root, a fourth root, a sixth root, an eighth root, then yes, you'll do plus or minus. But if you do an odd root, you do not have to do plus or minus. So this is my answer. Now I could try and figure out what that is in my calculator, but I'm going to leave it as an exact answer. What I do know is that the cube root of 128 is a positive number. So let me see. If I try and take that answer and plug it in there for x, well, that should be fine. That's the only x I have here. So log base 7 of cube root of 128. Yeah, it should work. So this should be my only solution. Okay, questions? Moving along. Last two. Okay, so let's do number 42 first. All right. What the heck? I have log on the left of x minus 1 equals 1/3 log 2. Right now, I cannot just set the insides equal to one another. I can't do that. And the reason I can't do that is because I have a 1/3 out here. That 1/3 can't be there. You have to get rid of it. So the only real option is to take that 1/3 and make it a power. So I'm going to do log x minus 1 equals log 2 to the 1/3 power. Now remember, that really means just the cube root of 2. That's all that is. When you raise something to the 1/3, it means the cube root. If you raise it to the 1/2, it's the square root. So that's not bad. Now I can set them equal to each other because I have the same log on both sides. So I can just set the inside here equal to the inside there. So I get x minus 1 equals the cube root of 2. And then I'll just add 1 to both sides. So the cube root of 2 plus 1, which is some number. I don't know exactly what it is. I could get my calculator out. Do you all know how to do the cube root on your calculators? Just to make sure you do. What is the cube root of 2? Let me see. Let me tell you what I get. I get 1.25992 something or another. So make sure you can get that on your calculator. What I did on mine is I did 2 raised to the fraction in parentheses 1 divided by 3. That's how I got that on my calculator. And I realize that all of you probably have a square root key on your calculator, right? To do the square root of a number. when I do square roots, I actually don't do that. Like if I wanted the square root of 5, I don't use my square root key. What I actually do is I type in 5 raised to the 0.5, because the square root means raising it to the half, and half is 0.5. So like whenever I'm doing square root of 5, I just go 5 raised to the 0.5. I'm just telling you that's because it's, I guess it's more general. You can use this for any root. If you had the 4th root, you could go 5 raised to the 0.25, or you could say 5 raised to the 1 divided by 4, depending on how you want to do it. Just make sure that if you're going to do a fraction, you put this in parentheses. Okay, let's just check our answer. Will that work? If I take cube root of 2 plus 1 and I plug it in right here for x, right there, that answer, it should work. Because I'm going to take that number, I'm going to subtract 1 from it, which will still keep it positive. So I should be good. All right, not too bad, I don't think, no. Ooh, what the hell? Whoa, this problem is weird. That's strange, huh? Look at that one. Huh. This is really different. What's real different about this one is this right here. Okay. Because the square root means we're raising something to the half, right? So I just want to take a moment to come over here and just talk about what this is. The square root of natural log of x, that is the same as taking natural log of x and raising it to the half. Would you all agree with that? It's okay. However, this is not, and this is where most students make a mistake, this is not equal to 1/2 natural log x. Remember the property I was just talking about with Dominic, about that property that's so important that you could pull powers out? That property does not work here. Now here's why. It's subtle, but it's important, all right? Compare that to this expression. What if I said the natural log of the square root of x? Now that's different, right? This is natural log of x to the half. And yes, you can, in that case, pull the 1/2 out in front. And so the big difference between those two expressions and why you can and cannot do it with the half is what the half, what is being raised to the half. So in the first example, the thing that's being raised to the half is the entire natural log expression, right? It's the whole expression to the half. The only way you can pull the number out is if the half is acting on the argument, the x here, then you can pull it out. But if it's acting on the whole log, you cannot. Does that make sense? Be very careful with that. So that means that we cannot easily do this, all right? So ready for this? Get ready, because this is gonna lead us into the next type of equation we're solving today. This first one that I do here is gonna kind of blow your mind a little bit. You ready? Watch. I'm gonna do something we have not done up to this point. I'm going to make a substitution. Okay, a substitution. What? I'm going to let u be equal to the natural log of x. Okay, that doesn't seem very natural, but let's try it. All right, let's try it. I'm going to let u be natural log of x. And after I do this problem, we'll go back to the beginning of it again, and we'll talk about why I did it. Maybe it'll make more sense why I'm doing this. If I replace natural log of x with u, let's see what we would get. We would get, well, this first one, that's just u, right? Okay, so I have u minus 3 times, now the yellow part is the square root, right? Square root of the natural log of x again, which is u, plus 2 equals 0. You all right with that? What do we do? This is weird. What about this? I'm trying to decide which path I want to go down here. Yeah, let's do this. Do you all agree that this first u could be rewritten? Could be if we wanted to. It's not very natural, but it could be rewritten as the square root of u squared. Isn't that what u is? It's the square root of u squared. And yeah, that's odd, but just keep following me here. Square root of u squared minus 3 square root of u. Do y'all see we have a square root of u in both of these now? See, these both have square root of u. I'm going to make another substitution. Watch. I'm going to let, I can use any letter. I'm going to let v be equal to the square root of u. So everywhere I see a square root of u, I want to put a v. So what does this new equation become?
V squared minus 3v plus 2.
Mm-hmm. And then what type of equation is that?
Quadratic.
Quadratic, right? It's a quadratic. Can you factor it? How would this factor? V, what would we need here? Two numbers that multiply to be 2, but add up to be -3.
-2 and -1.
-2 and -1, right? -2 and -1. Good. Now we can set each of these equal to 0, can't we? And we would get two solutions. We would get v is 2 and v is 1. Remember, I'm going to go back to the beginning of this and talk about why I'm doing it, all right? But we started with an original equation and we're trying to solve for x, right? We're trying to solve for x. And now at the very end, we're saying v is equal to 2 and v is equal to 1, which means we're not done. That's like me asking you what your favorite color is, and you tell me 7, right? Like 7's not a color. Like we're asking for the solutions, what's x, right? And you're telling me what v is. It doesn't make any sense. We have to go back to figure out what x is. So I'm going to go back now and I'm going to figure out, okay, well, what was v? V, we said was the square root of u, right? So everywhere I see a v, I'm just going to replace it with square root of u. That equals 2, and the square root of u equals 1. All right, great. Can you tell me what u is now? How could you solve for u on this? What would you do to get rid of that square root? Square both sides, right? Square both sides. So if I square both sides, I'm going to get u is equal to 4. Do the same thing over here. Square both sides. We get u is equal to 1 squared is still 1. All right, so we squared both sides there. So now I know that u must be 4 or u must be 1, but what was u? So go back up here. U was natural log of x, wasn't it? Natural log of x. So that means that I make another replacement that's natural log of x equals 4, and this one replaced natural log of x equals 1. How do you solve for x here?
Would you divide both sides by the natural log?
Careful, careful. Remember, natural log's not a number. It's not something we can divide on, right? So let me ask you this. What if I did this? Log base 2 of x equals 3. How would you solve this? How would you solve for x here?
The loop?
The loop, right? Okay. So how would you solve these? Think about the loop on these. What's the base of those logs?
E.
E and E, right? So do your loop. And what would this one tell you? E to the 4th equals x, right? That's one answer. And this one, e to the first power equals x. So e to the first power equals x. These are my two potential solutions. E to the fourth and e to the first. Let's check them. If I plug in to this right there for x, e to the fourth or e to the one, those are both positive numbers. Same here. So they should both work. All right, I want to go back and look at this in the very beginning. How in the hell are you going to know to do this, right? Well, that square root again, right? That square root really kind of eliminates the simplicity of the problem. It makes it complicated because you can't do this property. So you have to now realize, and this is like in hindsight, okay, you have to realize that if you squint your eyes, right? If you squint your eyes, kind of look at that yellow, I mean, the green, this looks kind of like a quadratic. Think about what a quadratic looks like. Quadratics look like this, ax squared plus bx plus c, right? So when we can factor quadratics, the pattern is this. There are three terms, 1, 2, 3, right? Do we have three terms? Yes, 1, 2, 3, right? We have three terms. Okay, so that's the first thing that tips you off. We have numbers in front of everything. So we have a 1 in front of here, we got a -3 here, and we got a 2 by itself. So we got numbers. And then here's the big thing. Whatever this x is, this is that thing squared. So if we look at this, this right here is being kind of like the x. If we square that, we get this, right? If you square that square root, you get that. So that's what made me want to do substitutions, right? It's a tricky problem, and there's other ways to do it. You could have, on the right here in this red equation, you could have treated this like a square root equation and isolated the root and squared both sides. You could do that. You could also have made a bigger substitution, but let's just stick with that, okay? Put a little star next to that problem. Make sure when you do the homework problems, let me look at the homework problems real quick. This was number 44. So number 43 is going to be similar to that. I think 43 is a little more obvious, though. This one looks a lot more like a quadratic. But just so you know, 43 works the same way that 44 does. You have to do a substitution. See how that goes. Okay. We are done with logarithmic equations. All right. The title of this section is Exponential and Logarithmic Equations. So now we need to start looking at exponential equations. So notice that for these first two problems, there's no logs involved, right? There's no logs. These are just exponential, meaning that the thing we're solving for, the thing we're trying to solve for, x, right, is up in the exponent, right? The x is up in the exponent. So we want to solve for x. That's what makes this exponential equations. The way, the general way to do this is to use a logarithm. Okay, so you know how when we had a logarithm, we used the loop? Here, we're going to go backwards. It's like this equation is already, the loop's already been done. We need to go back to the logarithmic version. So if I rewrite this as a log, it would be log, the base would be 5, this would be 25, and the other side would be -x. So just check for yourself that if you did the loop right now, right? If you did the loop, when you did the loop, you would get back this equation up here. Do y'all agree? Yes? So now that we've got this, we need to figure out what the left side is. And there's kind of two ways to do the left side. You either mentally do it or you use your calculator. So in this one, I can do it mentally because what this is asking me is 5 raised to what number is 25? So I know that 5 squared is 25, right? So this left side becomes a 2. And then that equals the other side, negative x. So the last step is just multiply both sides by -1, and you get x is -2. Now, I have good news with exponential equations. You do not have to check your answers like you did with logs, because exponential equations don't have the same domain restrictions. But let's just check it real quick. Does -2 work here? So if you go 5 raised to the -2, -2 would be +2. So 5 squared is 25. Yes, that's true. Let's look at the difference between that one and the one number 48. With 48, we're going to rewrite it as a log. It'll be 3 here, 14, and then x. So just double check mentally with the loop. 3 raised to the x is 14. Yes, that matches the original equation. The problem or the difference between this one and the previous one is, in the previous one, I knew that 5 squared was 25. Here, 3 raised to a power needs to be 14. I don't know any powers that I can raise 3 to, right? 3 squared is 9. 3 to the third is 27. So I don't know. I don't know what that is. So how are we going to do that? Well, we're going to use that last, one of the important properties again from last class. Let me get to them. Number 12, the change of base formula. I'm going to use this. Let me grab the whole property. So this formula, what it allows you to do, come on, there we go. What this formula allows you to do is use your calculator to solve any log. Let me just put it right there. Okay, it allows you to solve any log. So for us, we're doing this, right? Which is this part here. So what this is going to turn into for me is the natural log of 14 over the natural log of 3 equals x. And now I can just use my calculator. I mentioned this to you. This is why your calculator only needs a natural log key. You don't need any other log keys because of this very important formula. Come on, man. 2.402. 2.402, I'm rounding, is approximately what x is, okay? Questions? All right. With just what I've given you, everybody try and do number 50. And if you finish 50, try 52. 52 is a little tricky, okay? Because of this, what's going on out here, but at least try number 50 and let me know when you're done with number 50. I'll relaunch this poll. Let me know when you're done with 50. I'm going to work it out silently. And then I'm also going to work number 52 silently. I want to see if you can follow it. All right. Any questions on the first one? Okay, the second one, you cannot convert that to a log because of the 0.3 out front. So the first thing I'm going to do is divide both sides by 0.3. Watch. So I rounded on the second one. It's actually 0.666 repeated, but I'm just going to do 0.667. Once you're here, it's the same as the previous problem. You're going to convert it to a log. So log base 4 of 0.667 equals 0.2x. You know, little side note here. You've probably noticed as I've worked through problems, and maybe I've mentioned this before, I don't remember. Sometimes I'll write things like 0.3 and other times I'll write 0.3. Have y'all noticed? Sometimes I put the 0 in front, sometimes I don't. Really, this is just personal preference. They're both the exact same thing. The reason why some people put a 0 in front of the 0.3 is so that you really notice the decimal point. Because sometimes if you write like 0.3 and you don't make your point big enough, people might not see it and they think it's 3. But if you put 0.3, then even if you don't see the decimal point, that just looks weird. Like you'd be like, why would you write 0? So it makes you kind of pay attention, like, oh, there must be a decimal there. That's it. That's the only reason you need to put a 0 in front. It's just so you can, really see the decimal. Just wanted to mention that to you. Okay, so yeah, now I'm here. I go on my calculator. I'm going to do natural log of 0.667 over natural log of 4. That should be equal to 0.2x. And let me get my calculator here. So I get negative 0.292. Yeah, good enough. Is approximately, this became approximate as soon as we rounded that 0.666 forever. It should, it should really technically be approximate the whole time here. But let me take that number, negative 0.292, and divide it by 0.2. And I get negative 1.46 equals x. Questions on that? Okay. I move on, yeah. Oh, okay. All right. So now, we're slowly starting to add complexity. If you go back and you look at, this is exactly what happened when we did log equations last week. We started out with a simple log, just do the loop, right? Just do the loop. And then we slowly added layers of complexity. That's exactly what we're doing here. We're starting with basic exponential equations where you just convert it to the log and then use your calculator. Oh, we had to divide both sides first, then go to your calculator. Now we've got the x that we're trying to solve for is up in the exponent on both sides of the equation, which means you cannot, okay, you cannot do a loop. All right, you cannot do a loop. So things are about to change. You ready? Here we go. There's so many different ways to do this. I'm trying to think, do I want to show you? I'll show you two ways, all right? I'll show you two different ways and you can kind of pick and see which one you like better. So the first thing I'm going to do, and it's again, not going to seem very natural. What I'm going to do is I'm going to look at the bases on these. I have a 2 here and a 5 here. I'm going to pick one of those. So I'm going to pick the 2, all right? I'm going to pick the 2. And what I'm going to do is I'm going to do log base 2 on the left side of the equation and log base 2 of the right side of the equation. So basically I took log base 2 on both sides of the equation, which I'm allowed to do. It's an algebraically, it's allowed. And that really comes, what this comes down to, if you want to know, like, why are you allowed to do that? It's this, it's that property 13 again. Where's that property 13? That property 13 that we had right here says if you have log base a of x equals log base a of y, that means the insides are the same. What we're doing is we're actually starting with this and converting it backwards. So let me show you that. It's like we started with x equals y, and then I just did the x and y inside the same log. Now, why did I do that though? Let me show you why. The reason I did it is because this first log now just becomes x plus 1. Because what happens is that the log base 2 along with the 2 kill each other off. They wipe each other out. Now, why do they wipe each other out? Because of property 8. That if you have the same number here and the same number here, if these two numbers are the same, then all that happens is this just drops out. The power just drops out. That's why I brought in the log base 2, is I knew that when I put it together with the 2 to the x plus 1, they would kill each other off and just drop the x plus 1 out. Does that make sense?
Could you have put log base 5 and then it would have canceled out the other
It would have
one?
canceled the right side, but the left side still would have been there. Yeah.
Okay.
Yeah. Yeah. So I could have done log base 5, but I chose log base 2. Okay, let's see where we go from here. So now we're here. It doesn't look like we gained much because that still looks complicated, right? Still looks complicated. However, let me write it backwards and maybe it'll make more sense. All I did was switch the equations so that the right side's the left and the left side's the right. Okay. Now, you might be tempted at this point, you might be tempted to do the loop. But what's wrong if I do the loop?
You're just gonna go back in a circle because it'd be 2 powered by the x plus 1.
Yep, if I do the loop right now, like this, I'm going to go right back to the original equation. So I will have basically done nothing, right? Just wasted my time. Yeah. So shit, what do we do, right? This seems like we're caught in this loop, but watch. This right here on the left-hand side, just agree or disagree with me here. That could be rewritten as natural log of 5 raised to the 1 minus 2x over natural log of 2 equals x plus 1. Okay, what did I do? What the hell did I just do? Why is the left-hand side this? What am I using? What am I using to do that? Isn't that formula 12 again? If I have log base a of something, it's the log of that something over natural log of that something over natural log of a. So I was basically looking at this as, you know, log base a of x, and I rewrote it as natural log of x over natural log of a. Do y'all see that? That's formula 12. Well, why did I do that? Let's see why that actually works. Okay. You ready for the next step? Look at this 1 minus 2x. Isn't that the power on that 5? Sorry, that's the power on the 5. And there's a natural log in front of that. So can't I bring powers out in front like this now? I'm allowed to do that. That's a property. That's property 9, or wait, 9? Property, no, 11, sorry, property 11, right? Powers can come out. So I'm going to bring that power out. So watch what my next line looks like. It's 1 minus 2x times natural log of 5, all of that divided by natural log of 2 equals x plus 1. Yikes. Now, this is a number I can get on my calculator. Let's do that. Oh my gosh, what is going on with my phone this morning? Take the natural log of 5 divided by the natural log of 2 and get a decimal answer. You should get, let's see, 1 minus 2x is still here, but those two divided together give me times 2.322, I'm rounding, equals x plus 1. Questions? I realized like we jumped pretty quickly into something weird, right? With this. This is a linear equation. You can just distribute this number through the parentheses now. So that's 2.322 minus, now I need to multiply 2.322 times 2, so 4.644 x equals x plus 1. And now this is just a linear equation. So you can just move things around. Like get all your x's on the right, get all your numbers on the left. So I'll subtract 1 on both sides. And I will add 4.644x on both sides. You should get 5.644x. Do I need to show that step? Do y'all understand what I'm doing there? Does anyone need to see that? Subtracted 1 both sides, added 4.644x on both sides. Now I'm going to divide both sides by 5.644. And I'm getting 0.234 is approximately what x is. Wow. That was weird. So I told you I would show you this 2 ways, right? I'm going to show you it a different way now. So what I'm trying to illustrate with me doing this a different way is that what we realize by doing it this way is that at the end of it all, we're going to wind up with natural logs, right? Because we're going to have to use a change of base formula. So the way we would go about this, okay, like after you've been through college algebra, right? If you were in a calculus class and you saw this equation, here's the way you would do it, all right? You would not do what I just did. You would do this. You would simply take the natural log on both sides of the equation, the natural log. So I wouldn't even do log base 5 or log base 2. I would take the natural log on both sides. Now, why do I do that? Because these powers on both of these can pop out, right? Like that. Okay, so I get x plus 1 natural log 2 equals 1 minus 2x natural log 5. Y'all with me? Now, I'm just going to divide both sides by natural log 2. And on the left side, it goes away. I get x plus 1. And on the right side, 1 minus 2x. I would do on my calculator this, right? Which we just did earlier. That was times 2.322. Does that equation look familiar? That equation at this point, right? At this point right here, we are actually at, where was it? Right here. It's that point. Do you see that we got to this equation? Actually, we got here, right? Right about here, without having to do all of this stuff. We didn't have to do all this and that. We didn't have to do it, right? So going back and looking at this in hindsight, right? We say, okay, the x we're trying to solve for is on both sides, it's up as a power. So what I'd like to do is just take natural log on both sides. And then that'll allow me to pull my powers out, and then I can deal with the natural logs on my calculator. All right. See if you can, well, do you think you're ready for it? Do you want to try number 56? Or should I do 56 and let you do 58? You want to see one more? You see one more? Yeah, okay, one more. Okay, so look at number 56. I've got some number, right, raised to a power, and my x is up there, right? Then I've got some other number, 5, raised to some power, and I've got an x up there. So my x's are in the powers on both sides of the equation. So I should be able to just take the natural log on the left and take the natural log on the right. And that will allow me to pop the powers out front. So when I pop this power out, I get 1 minus x times natural log of 4/3 equals x times natural log of 5. So I've used the property that I can pull the powers out. Remember, those powers can only come out after you've brought the logs in, because that's a logarithmic property. You can't pull powers out in front just, for fun anytime you want, right? Like when you write the number 4 squared, you can't say, oh, just pull the 2 in front and make that 2 times 4. It's not the same thing. You have to have a log in front to do that. Okay, now what I'm going to do is I'm going to divide both sides by natural log of 4/3. And that I can get my calculator for. It'll go away over here. I'll get 1 minus x equals x times. Now I get on my calculator. Be really careful, because that 4/3 is inside that log. So make sure on your calculator you can get this answer that I get. This right side, all of that together, you should get 5.595. I rounded that last decimal. Make sure you can get that on your calculator. And really, this is just a nice little linear equation now. I can put that 5.595 in front of that x instead of behind it. add an x to both sides. So that will give me, I don't want to work there. That'll give me 1 equals 6.595x, because I'm just adding 1x to 5.595 x's. And then divide 1 divided by 6.595 is 0.152 is approximately equal to x. Now I realize you're sitting here going like, why are we solving these equations? Like when, how is this useful? Next class, we're going to do applications where you can actually see why we would do this, all right? Right now, we're just trying to get the mechanics of it down. Okay, you try number 58. Let's see how you do with number 58. I'll relaunch the poll. I only want to give you like maybe 4 minutes. See how far you can go. Okay, another 35 seconds. So far, only one student's done. Okay, now I'm sharing my screen and you can see the solution. See if you follow that. Give you maybe 30 seconds to look at that. All right, so you can see how important it is to, when you bring these things out front, if you have two terms, to make sure they're in parentheses, especially when you do the division on your calculator, you're going to get a decimal, and that decimal must distribute through this parenthesis. If you forget the parenthesis, it's going to be an issue. Who has questions?
How did you get the negative 0.559?
What did I do here? Oh, so I added this to both sides, so that gave me 1.882, and then I did 0.441. I subtracted 1 on both sides. Yeah, so on this one I subtracted 1, and here I added 0.882x, added 0.882x. Is that not what you're getting? I think 0.44.
I got it now.
You got it. Okay. Yeah, you do have to be careful when you do the natural log of 1.7 over natural log of 0.3 on your calculator. You get a negative number, and then that negative number distributes, which changes the signs to negative, then positive. Any other questions? No? Okay, I'm going to move on. Look at this one. This looks weird. E to the x plus 3 equals pi to the x. I have x's on both sides in the exponent. The bases are numbers, right? E is a number, pi is a number. Okay, fine. I'm going to bring in the natural log. I'm going to pop the powers out front. All right, now I should divide both sides by natural log of e, right? That's what I should do. But does anyone remember, this was an important property. What happens when you put natural log and e together? So let me go back to last
They
class.
cancel out?
They cancel out, they become a 1. Where is it? Right here. See it highlighted in blue here, right here? The natural log of e is 1. So really, this is a 1, which means I can just go straight to the next line, which would be x plus 3 on the left equals x times natural log of pi. So I don't have to divide through, but I do need to figure out what natural log of pi is, and that I will need my calculator for. And that comes out to be x plus 3 equals, and then that becomes 1.145, I'll say, x. So natural log of pi is about 1.145 times the x, so I put it in front of the x instead of behind it. And now what I'll do to solve for x is I will subtract x on both sides. That'll leave me a 3 here equals just 0.145. See, I put a 0 that time, didn't need to, but. And then finally divide both sides by 0.145. So you should get like 20.689, actually 0.69, whatever. We won't worry too much about the rounding. Questions? All right, we're moving on. Whoa. So we've got a problem. We got big problems here. We've got our x up here, we've got our x up here, but notice we have a new term in here, -2, that does not have an x. So, and it's equal to 0. So even if we tried to like move this to this side, right? To try and be able to do the natural log on both sides. The problem is this -2. So this problem is like apples and oranges compared to what we've been doing. So again, you got to see this for the first time, all right? Ready? Check this out. Do you agree with this? The first term could be rewritten as 3 to the x squared. So I'm using a property that if we have x to a power to another power, we multiply the powers together, right? So if I have a 2 times x right here, I could rewrite it as 3 to the x, but then squared. And then you would multiply the x and 2 and become 2x. So that's just another way of writing it, right? That's all that is. But by doing that, can y'all see that this looks like that quadratic thing we talked about a minute ago with logs when we did the substitution? Remember this thing? Oh, we got to see that it looks quadratic and we can make a substitution. It's that same sort of thing here. We want to realize that this right here is the thing that's like the x. This is like the x and this is like the x squared. So we're going to make a substitution letting u be equal to 3 to the x. So everywhere I see 3 to the x, I replace it with u. That turns this into u squared plus u minus 2 equals 0. So everywhere I see a 3 to the x, I replace it with u. I leave the -2 equals 0 alone. That's a quadratic. It actually factors. Thank goodness I don't need the quadratic formula for this. And that gives me 2 solutions. -2 and +1. Now, those are my answers for u, right? But u, remember, u was 3 to the x. So I now need to replace the u with 3 to the x equals -2. Replace that u with 3 to the x equals 1. And now you're back at the first problems we did with these today. You can just rewrite this log base 3 -2 equals x using the, if I do the loop, right? If I do the loop, I'll get back that equation. 3 to the x is -2. And then this one would be log base 3 of 1 equals x. So 3 to the x equals 1. And then I'll use the change of base formula and I'll use my calculator to figure out these. Right? I'm just using that property where you can switch this using your calculator. So I'm going to get on my calculator and do natural log of -2. Uh-oh. What happened? I put in natural log of -2 on my calculator. I got an error.
You can't be
Right.
negatives.
That's right. It can't be negatives, which means that we have no solution from this. You can't plug -2 into your calculator. And then on this one, when I do that, you should get 0 on the left-hand side equals x. So that's your solution. That's your only answer. Can we check this answer real quick? I know you don't have to, but let's just check it. 0. It'll be easy to check. If I replace this x with 0 and that x with 0, let's see what we get. We get 3 to the 0 plus 3 to the 0 minus 2 equals 0. But 3 to the 0 is 1 plus 3 to the 0 is 1, and then minus 2, that equals 0. Yeah. 1 plus 1 minus 2 equals 0. What's important here is for you to look at this problem now and say, you know what? I see that it could be possible that I get a quadratic looking thing here and have to do substitution. Let me look at the next one. Not quite ready for that one. Not quite ready. This one's a little tricky. Let's do this. Let me look at the homework assignment. Okay, that one that I was looking at, yeah, these get pretty common. 64. So why don't we do this? For your homework for tonight, I want you to continue this. We stopped at 21. Let's go ahead and look at the odds here. Those are all going to be log equations, right? So the yellow ones, those are all log equations. Based on what we did today, you should be able to handle those odds. And then the exponentials start, and you should be able to handle, let me see here. You should be able to handle those. Stop at 61. So you're basically doing 23 through 61 odd for tonight's homework. I'll leave that up there, or sorry, yeah, 23 through 61 odd. I know that's a lot of problems, but practice. I forgot 27. Okay, we still have a little bit to do in this section, so we'll see how it goes. And that means we'll probably only have maybe, we'll probably use maybe out of next class, we have 100 minutes for each class. So we'll probably use the first 30 minutes to 40 minutes to finish up the rest, which won't leave us a ton of time for application. So we'll get maybe just a few applications of this that would be on the test next week on Monday. Okay, any questions? That's the homework. Just ignore anything, on the online system. Just do these problems and then come with questions if you have any next time. All right, do your homework. Have a good day.
Bye, sir.
Thank you.
Yep, I'll send these notes out right now.